This is the electric bike that I just built. And this is its battery. EV batteries may look dangerous sometimes. But in this video, I will show how I built a safe one. Or at least tried. Battery packs are composed by four major groups of components. The first one of them are the battery cells. The second one is the connection between the cells, or the busbars. The third one is the balancing management system, or the BMS. And the fourth one are a bunch of minor things that we can say that are the others. Let's start talking about the most important one of them, that are the battery cells. The first thing really important to understand is that battery cells are not all the same. Look into them, the shape make it a little bit clear, but the main important thing is inside of them, that's about the chemistry of it. The different battery chemistries really impact the characteristics of it, and the major ones are the temperature range, the C rating, that is the charging and discharging current, the energy density of it, that's the amount of energy that's stored in a certain volume of batteries, and the two that I believe that's the most important ones, that is the cost and the risk of it of catching on fire. That is a pretty nasty thing. To try to help you to choose which one is better for you, I made this graph. In one side of it, you can evaluate the risk of it catching on fire, that I will call here the holy risk. In the other side of it, you can evaluate the cost that it will have. For each battery chemistry, you have a point in the graph that also show you the usual temperature range, energy density, and C rating of the chemistry of this battery. Let's use the nickel manganese cobalt batteries, or NMC, as an example. I added an extra remark about the whole risk. Now we can position this battery in the graph, add the lithium-ion family, add the lithium polymer, the nickel family, the sodium batteries, and the lead-acid ones. Now is a perfect time for a screenshot. Well, I don't have an actually perfect battery chemistry to indicate for your application, because depending on it, it may vary. In my case, the lithium iron phosphate was the most suitable one for my application. Well, now that we decided which kind of chemistry we will use to build the battery pack, it's time to decide how many of them we need to connect to get the proper battery pack working. Usually, we have some common volt outputs for battery packs, and it can go from 20 volts to 72 volts. For my application, I choose to go with 48 volts. And for lithium iron phosphate batteries, we need usually to connect 16 of them in series to get the 48 volts package. Well, actually, as each one of the lithium iron phosphate batteries have a nominal output of 3.2 volts, and we had 16 of them, the battery pack will have 51.2 volts of nominal output. And now we can adjust the information here. Another important point for our battery pack is to define the capacity of it. A good way to define the capacity of your battery pack is to see the average of the usual commercial vehicles that we see on the market. Let's take as an example cars. They are on the heavy side of EVs, and they usually have a battery capacity from 30 to 82 kilowatt hours. Motorcycles, for an example, weigh a lot less than a car, and they usually have 3 to 10 kilowatt hours of battery capacity. Mopeds are an even lighter version of a motorcycle, and they usually have 0.5 to 3 kilowatt hours of battery capacity. In my case, I wanted to design a battery pack with 1 kilowatt hour. And the capacity of a battery pack is defined for the capacity of each series of it. Let me explain. To know the needed capacity for each one of the series of this battery pack, that we want to have 1 kilowatt hour or 1000 watt hour, we need to divide that by 51.2, that's the nominal output of the battery pack, and you get something around 20 amp hour. This means that for each series of this battery pack, I need to have a 3.2 volt battery with 20 amp hour capacity. To get this battery capacity, I can use a single cell of 20 amp hour, but that's exactly the same that using, for an example, two batteries of 10 amp hour, each one connected in parallel. Or to use 10 batteries of 2 amp hours each one connected in parallel. Any one of these configurations will give us the 20 amp hour that we need. In my case, I decided to move forward with a single cell of 20 amp hour each one. That way, I don't have a bunch of parallel connections to do, and the battery pack will be much more simple to build. So, just a recap. The chosen battery cells are a lithium iron phosphate battery that have a 3.2 volts nominal output, and each one of them have a 20 amp hour capacity. This specific battery has a 3C nominal discharging capacity. That means that it can output 3 times its own capacity as a discharging rate, or 60 amps. If we multiply it by the 51.2 volts of nominal output of the battery pack, we got the power output of it. That is 3 kilowatts. This must be the same power of your motor or load that you are intending to use in this battery pack. These battery cells always can handle a 5C peak discharging, which means that it can handle up to 5 kilowatt, but just for a short period of time. It also has a 0.5C nominal charging capacity, and each one of the cells cost me around $11.7. As I have 16 of them, the total cost for battery cells was around $187.2. Well, this cost does not include taxes or freight because it's too specific for your region, but it's a good starting point. Well, now that we decided the chemistry of the battery cells that we are going to use, we can move forward to deciding what will be connecting them together, or the busbars. Well, they are usually made out of copper, nickel, or aluminum, and can come in two different formats that are metal strips or usually thicker screwed in place busbars. The strips usually are welded in place using a technique called spot welding. Spot welding machines usually are quite expensive, and in my case I try to avoid using them. That's why the battery cells that I choose have a place to screw a busbar in place. Busbars can come in different sizes, and usually as it grows, the capacity of conducting energy also grows. Well, I have a personal general rule to choose the busbars. Let's take the peak current of the battery pack that's 100 amps. I added a factor of 50% or multiply it by 1.5 and get the result of how many amps my busbars need to handle. That in this case is 150 amps. You may be wondering that the 150 amps is a little too much. But you don't really want that your busbars are your weak spot of your battery. Busbars are really inexpensive and it's worth it to invest a little bit more. If your busbars can't handle the current that's passing through them, sometimes they may heat. And a source of heat in your battery is not always too good. Well, now that you know how many amps your busbars need to handle, you can select your favorite busbar supplier that usually you can find online and ask them to a chart to choose your busbars, mostly like this one. These charts usually will have different size of busbars and how many amps they can handle, and you just need to take a look and choose the best one for your application. And talking about cost, until now we have the batteries and the busbars that cost me around $18.9. Well, now that we choose the busbars that we are going to use, we can proceed to choosing the brains of the battery pack, that are the BMS, or the Balancing Management System. The BMS is the main source of protection of your battery pack. To understand why a BMS is important, first we need to understand how a battery charges. The volts measured in a battery cell may vary during the process of discharging and charging of it. For lithium iron phosphate cells, usually these numbers get around 3.2 volts, but it can get as low as 2.5 when we have no charging at all on it, or it can get as high as 3.65 volts when it's 100% charged. Let's take an example of a battery pack working without a BMS. As we saw, each battery can get up to 3.65 volts. So usually a charger to this battery pack that had 16 cells outputs 58.4 volts. If we get a package with no charging at all and connect the charger on it, it will start charging the batteries. But as we saw, batteries are chemical devices, and sometimes they are not perfect. If one battery charges faster than the others, it may get to an extreme point. But as the state of charge of the battery pack do not reach the same volts as the charging is outputting, it will keep receiving energy, and it's not hard to think what will happen here. To To try to solve this problem, we can use a BMS. The BMS works putting an upper and a lower limit of charging and discharging for each individual cell. This way, any battery cells will ever overcharge or over-discharge. Even if we have unequal cells that charge or discharge faster than the others, it will always have a limit for it. So the battery pack will always safely charge and discharge. The BMS that I choose for this project is a BMS from a company called Dali. It's a 100 amps smart BMS that allows me to connect with it through Bluetooth. So I can check a bunch of interesting things like the battery temperature, the battery charging of each one of the cells, the state of charge of the whole battery pack. And it also led me to program a bunch of features like the maximum charging and discharging current that it will allow me to do. So talking about cost, now we add the BMS to it, and it cost me around $68.6. Well, now that we choose the most important parts of the battery pack, we have a bunch of minor things to choose that I call here the others. I call it this way because it really depends on the design that you are planning to this build. For an example, battery cells usually have common brackets that can put them together. But in my case, I needed to design custom ones using 3D printing. You also will need a couple of connectors that you must decide which one are better for your application. The enclosure of your battery pack also may vary. The one that I built for myself needed to be 3D printing because of the geometry of it. For putting everything together, a good rule of thumb is to follow the BMS manufacturer orientation. Usually BMSs come with a manual of instruction on how to do it. But you may be wondering that this whole thing of math and designing a battery pack to choosing the components of it, it's a little bit too complicated. So to make your life a little bit easier, I made a calculator that can help you. All that you need to do is to input the characteristics that you'd like this battery to have, and it will output all the components that you must buy. The link for this calculator is in the video description. The components that I used to build this battery pack is also in the video description. You may be wondering that this battery pack is not so big, so the autonomy of my EV is not so big as well. And you might be right. But this battery pack was not designed to work alone. It was designed to work with a bunch of supercapacitors. And my expectation is that this supercapacitor can give a little bit of an extra range to my EV. If you think that it is interesting, keep tuning on my channel because this is the next video that I will be posting here online. And now talking about the cost, we can finally add the cost spent with the others. And it results in a cost of this battery pack roughly $350. And if this video helped you in some way of how to building a battery pack in a better way, or you learned something new, it's a good time to hit the like button and consider subscribe on the channel. See you, have a safe ride.